So let's go in, and what I want to talk about, I'll do my little example here. Now, the thing about this example is that we can figure out all the answers, just by reading and looking at the example, okay? And that's true. However, what I want to do is I want to practice the techniques that I'm trying to introduce, where we're going to pick a coordinate system and utilize that in order to calculate our quantities. And so that you can see how to do that, because you want to practice when you actually kind of understand things, doing these new techniques or whatever. And so then what will happen is so that when you get to the problems where you can't just look at it and figure it out, well, you're like, well, I'm just going to follow the technique. I'm going to pick my coordinate system. I'm going to load my stuff, and we're going to go from there. Okay. And so in this first part of the example, I'm going to call that case 1. So in our first case, we're going to have our person is going to, walk in a straight line. They're going to do 10 meters. They're going to go to the east. And then in the second portion of the motion, they're going to do 5 more meters east. Okay. We're going to claim that no matter what happens, that the amount of time to go from the very beginning to the very ending is just going to be our, I don't know, we'll make it 5 seconds. So everything's nice and pretty and even, okay? And we can go in, and in the second case, I'm going to have our person, and they're going to move 10 meters east. But then they're going to cut back 5 meters west. Okay. And so what we can talk about is we can go and talk about all the different types of quantities we've introduced so far. We can go ahead and talk about, well, what was the distance traveled in each case? Well, they did 10 meters and then 5 meters, so traveled 15 meters. Let me make this an equal sign. This is also the same. Well, I'll come to that one in just a minute. So that's our distance. And then we could go in and we talk about our displacement. Okay. Now that displacement vector is going to go from where they started to where they end. I don't care how they actually moved. It's that shortest directed distance that goes from here to here. The symbol we use is a delta x. And we can go in and take a look at that the magnitude of that displacement's the 15 meters, and the direction's going to be east. Okay. And then once we have that, I'll come back to this in a minute. And then we can go and we can get our average speed and our average velocity. Okay. And so if we want to calculate our average speed, then that's our distance that was traveled, 15 meters over the time, which was just the 5 seconds. And so we get that this is our, 3 meters per second. And if we want to calculate our average velocity, then it's our displacement vector divided by the amount of time. And so we did, 15 meters east. And again, it took 5 seconds. Then what we get is, 3 meters per second east. Okay. Remember that when we take a vector and we multiply by a scalar, and dividing is the same as multiplication by the reciprocal, then what happens is that as long as the scalar is positive, then we just, manipulate the magnitude, the direction stays the same. Only if the scalar is negative would we reverse the direction type of things. So we found everything and we didn't have to pick a coordinate system, didn't need to do any of that kind of other stuff that I started talking about. And so this is exactly what I wanted us to see, is that this can be done like that. But we can also go in and we could also choose our coordinate system. So now normally the way we would do this is we would come in and pick out that our origin of the coordinate system is usually where we start. Usually a pretty good choice. And the reason that that's such a nice choice is because then my initial position vector is a 0 vector. Because we're right there, you know. We'll pick to the right to be positive, to the left to be negative. That means this intermediate location would be plus 10 meters, and that this final location would be plus 15 meters. And so again, to do the distance, we wouldn't really do anything different, but to do this displacement, we would go in and take the final position vector minus the initial position vector. And what we would get is that my initial position vector would be 0 because it's that 1-to-1 correspondence. And my final position vector would be coded in as plus 15 meters. Again, that 1-to-1 correspondence between this, final coordinate position and that position vector. And so then when we come in and we take our final position vector minus the initial position vector, we get plus 15 meters minus the 0 gives me plus 15 meters. And then the positive sign here would tell us the direction in this particular coordinate system, which would be that this was west, this is east. So this is going to tell me that it's east, just like we already knew. And so in calculating this average velocity, then what we would do differently is we would just do plus 15 divided by 5. Gives us plus 3 meters per second. And then, of course, that positive sign would then interpret as being the east direction. Okay. So, yeah, there we go. So did we need the coordinate system? No, not really, but it's good to practice, especially when we know how things are going to go. And that's going to be the big lesson for most of this chapter, is you're going to look at it and go, oh, I can figure this out. I don't need to do all the little techniques, but let me tell you right now that when we get to chapter 3 next week, that won't be the case. So if you don't know how to set things up and get practice when it's easy, then when it gets hard and you can't do that by reasoning it out anymore, you're going to have a real trouble. So practice now while it's easy. Okay. All right, let's look at our second case. And, we could go through the same argument, but I'm going to go ahead and practice with the coordinate system. So let's go in and we'll pick kind of a very standard coordinate system. We will pick that, to the right is going to be the positive direction, to the left is negative. And so this is the west, this is east. I'm going to put the origin of the coordinate system where our person originally started, so at our initial position. And then I'm going to go in, this intermediate position is the plus 10 meters. And then this final position, since we went backwards, is going to be plus 5. Okay. And so then with that, we can do our distance traveled. Well, that's exactly what we had before, is that it was 10 meters on the first leg of the journey plus 5 meters on the second leg of the journey, because the directions don't matter. And what we get is that they traveled a total of 15 meters. Okay. And now this one's going to be more interesting because previously it looked like the scalar values, the distance and the average speed, were essentially the magnitudes of our vector quantities. Okay. But that will not be the case here. And so when we come in and take a look, then my, initial position vector is 0. And then the final position vector, again, there's that correspondence, is the plus 5 meters. And the displacement's going to go from where we start to where we end. I don't care how you actually moved. And our displacement's going to look like so. And we can see from the picture that's 5 meters and it's east. but we can also do the calculation in our coordinate system. So when we come in and do the displacement vector, or the change in the position vector, that is the final position vector minus the initial position vector, which is this, plus 5 meters minus 0 gives us plus 5 meters. And again, the plus sign in this case is going to indicate that it's, east. Okay. Now, when we come in to do the average speed, that'll be the distance that we traveled, which is our, 15 meters over the time that it took, which was the 5 seconds. So this gives us, again, 3 meters per second. And if we come in and we look at our average velocity vector, that's going to be our displacement vector over the time. So coded in the coordinate system, that would be the plus 5 meters over the 5 seconds, gives me plus 1 meter per second. And the positive sign here indicates the direction, because this is a vector quantity. You can tell because it's got the extra line on it. This is east. Okay. And so now what you see is that in these cases, this scalar, the distance, is not the magnitude of the displacement, and that the scalar average speed is not the magnitude of our average velocity vector. However, they were those in this case, but they are not in case 2. So the question is, why are they different in 2 than they were in 1? What happened? Guesses? Did I lull y'all off to sleep or something?
Sorry, for me at least, your mic cut out whenever you were asking the question. Can you
Okay.
repeat it?
I sure can. All right. So in case 1, we saw that the distance, which is our scalar, was the magnitude of the vector displacement. We also saw that the average speed, which is a scalar, was the magnitude of the average velocity vector. However, in case 2, they aren't. Why? What happened?
In case 2, you have motion in the positive direction and motion in the negative direction.
Okay. So let's put it one more way. Right? And there's another way to put it. And I think Olivia has it. So, excuse me. So what happened in the second case is that the person, as they moved, they changed directions. So just like you said, the positive motion, negative motion. So they changed directions. And because of that, these scalars are no longer the magnitudes of the kind of associated vector quantities. All right, so that's the important lesson out of our little simple example. And again, we got to practice, choosing the coordinate system and coding information in and how that's going to look and how that's going to go. And again, I think that in chapter 2, you're going to be in really pretty good shape, even if you don't happen to do that. But however, if we don't practice that now, then when we get into chapter 3, you're going to have a difficult time. Okay. So let me write down what we were supposed to note. So, because we changed directions, then our scalars are no longer equal to the magnitude of the associated vector quantities. Magnitudes. So only if the object continues to move in a straight line will they be related like that, like we saw in case 1. All right. And so now what we want to go in and talk about is want to talk about speed and velocity. And so that's the first thing we want to talk about.